Thanks so much for the introduction. I have to say, I'm not doing a lot of the work myself anymore. I have 3 teams, data science, Calval, and product innovation, and they're doing great work. You'll see some of the work also featured in this presentation, and I changed the presentation a little bit just from the feedback I got from you. So I hope you enjoyed as well, but for now we're going to space. Yeah, okay, I have to get used to the lag a bit. It's significant. Yeah, I'm not sure. Okay, so what you should see here is actually a video of the damage of the wildfires that happened in Greece in 2024. So I don't know how it was for you, but for me, wildfires were often a very remote problem, happened in Australia, Canada, but they happen in Europe right now, and they destroy biomass, ecosystems, livelihood of people. And what this fire in particular was, it was the size of a small tree, shrub, at 3 p.m. in the afternoon when it first got detected by a geostationary satellite. And when I talk about active fire detection, that's what I mean. So it's really the low latency detection of a fire before it grows into something significant. And when you work in fire progression modeling, you produce these forecasts. And I'm sure many of you have worked on forecasting yourself. And what you don't want to be in those situations, you don't want to be right. Because this is a fire spread that's catastrophic. Like the wind situation was really like there was a lot of wind, and that's what we forecasted. And unfortunately, in that case, we were close to how the active fire situation looked like a couple of hours later. And you've seen the damage in the video. And I wanted to bring this slide to you because people act on information you provide to them. So in this case, over 700 firefighters were being were deployed in the field, almost 200 vehicles, 17 aircrafts in the air, 8 helicopters. So people act on the information we provide them. And especially in disaster situations, they need to make decisions fast. I was living in California for the past month, and I was talking to a group of fire chiefs the other day. And when you're fighting a fire and there are evacuation zones, and you have to decide which people, like which evacuation zone you're going to, and you take all the information you have available from your phone. So I have contact to the dispatching center, but you also use your phone, and they use everything available because these are high pressure, high stress information, and everything counts. So everything you get your hands on counts. And I brought another slide talking about open science because I want to stress that we're frequently at conferences, and open science and open data availability is really important to me. So we're not publishing large papers at the moment, but we always have posters. We have a poster out here, and it's really important for me to keep the exchange with the scientific community and also contribute and learn from you. I mean, the best case, it goes both ways. And now you saw what we're now we saw how our situation looks like in the field, how our product looks like. So this was our software solution, how our customers sees the data. But this is who we are. So we're actually a spin-off from the Technical University in Munich. So if you're still at university, you're considering creating a company, we're a successful case of that. So we're over 170 employees on 4 continents, and we have over 300 users. And since last week, we have 11 satellites in orbit because we just launched our 11th, but we're integrating 27 different satellite sources. And we just heard from the other talk that creating such a data archive now has value in itself. So it's not just about providing the detection component, it's also about the data storage. And since Bertrand is here, and we're also really proud to be part of the Copernicus data provider, or of the Copernicus contributing missions program, becoming a Copernicus data provider. And you see us, so these are all the Copernicus missions. They're different stages. I'm happy to talk about it in a coffee break. But we're basically being onboarded into the European space data ecosystem for our data to be provided to researchers. And more on that in the end. But where we want to go towards as a company is high revisit of the globe. So we want to provide thermal imagery or active fire detections of the whole globe every 30 minutes. So we're optimizing for high frequency data, not high resolution data, because this is a design choice you make in the beginning. High resolution instruments are often a bit more bulky. You need larger telescopes, and they're also more expensive. And so if you want to scale to high frequency revisit, you can miniaturize your technology, and you're basically just launching a lot of satellites. Who did this before Starlink? I mean, this concept is known. So you go to more of the shelf hardware design, and then you just launch it in bulks. And that's where we're at. So we also built a plane for the Greek government, which is being launched end of 2025 or January. I think it moved a bit, but we already have plenty of assets in space, and we're planning to go up to 80 satellites, because then we're getting to this 30-minute revisit rate. And I have a geo and environmental science background, and it was always my dream to see Earth breathe in a way. So if you have a global Earth observation snapshot in thermal of the globe, you will see things that we have no idea that they even exist or happen. So that's why I'm really excited to work in this area. And but now you might say, well, there are a lot of satellites already out there. Why does another company need to build more? Well, there are none in the afternoon gap. So there's a window between 12 a.m. and 12 a.m., 12 p.m., 4 p.m., where there are very few satellites out there. That has reasons, because usually the transporter launches go until like to 11 a.m. or 1 p.m. And when you launch a mission that has to cater to a variety of use cases like Sentinel or others, you don't want shadows in your data, because like the zenith angle of the sun, it really influences data quality. But we want to go exactly in the afternoon window, because that's where most fires ignite. So for us, it's critical. We saw it in the beginning that fire ignites at 3 p.m. That's due to human activity. That's due to the soil heating up. So there are a variety of reasons why that's happening. That's our cute payload. So it has two thermal cameras and one RGB camera. That's the black one. It's called Sapphire 2. I won't go into details for you. What's relevant is that it has a mid-wave and a long-wave infrared channel. And I did not pay attention to the Alpha Earth input channels, but I'm not sure if you carry thermal infrared in the mid and long wave just now. But no, okay, then that's okay. Well, that's good. But the majority of the models do not carry thermal yet, and the data comes at a 200-meter resolution, but can recognize fires as small as 4 times 4 meters. So that's the sensitivity, the radiometric sensitivity of our payload. And this is how the data looks like then. So we're looking at oil fields, and this is the long wave infrared. So you can nicely see the difference between the landmass and the ocean. And in mid-wave, that's more sensitive to high temperature events, you can see the gas flares nicely lined up. So we often image constant thermal anomaly regions just to calibrate our algorithms, because usually for fires, you don't know when they happen. So we have the targets that we're frequently imaging to see if our algorithms work. And oil fields are actually a really good target. Then I wanted to talk about band specification. So here you can see our bands. So our filter design is being reflected in the part of the electromagnetic spectrum we can measure. So the mid-wave is for wildfire detection, and the long wave is for land surface temperature derivation. And on top, you can see all the other missions that are out there. The blue ones are planned, and black ones are the ones already existing. And what I wanted to share is that obviously the sensor designs are similar. So we have a spectrum we all cover, but they're very, very different in a way also. So we're not measuring the same thing if we have 2 optical, 2 thermal satellites. And I feel like often that's not being accounted for enough, that there's actually a lot of work and fusing those data streams together to have them represent the same conditions on our Earth surface. So the data products in thermal, sure, many of you work with reflectance. In thermal, it's a bit different. So you have radiance as the level 1 top of atmosphere data product. Then you have active fire detection as one data product that's derived, so thermal anomaly detection. And then you have land surface temperature derivation. So you correct for the emissivity of the Earth. and for the atmospheric radiative transfer. So, and this is just to share what we're working on, like this is the majority of our work, is to provide a consistent data quality. And that's being separated into geometric data quality and radiometric quality. And I thought I'll bring this here just so you develop some empathy for the downstream data providers, because we're being assessed by ESA or by independent research groups on geolocation. So if the pixel we claim to be at a certain point is actually at the point, and the band-to-band co-registration. So these are things we're optimizing for, and these are really tricky problems. And then, so this is the geometric accuracy or the geometric data quality component. And then there's the radiometric accuracy. And that means if the value you're deriving in Kelvin in our case actually resembles the values that other satellites are measuring or that we can derive through ground stations. And we're comparing ourselves against theirs. And we're actually pretty close by, like it's 2 Kelvin, which is something people told us we can never do with such a small instrument. Yeah, so now let's go to the applications. Here you can see the Palisade fire, so the fire in LA, and how active fire detections actually look like with an active fire front. So you have all those detections. And this is, I mentioned it earlier, our processing chain. So the satellite overpasses a certain region on Earth. Then we have pre-processing already on the satellite, have the fire detection running on the satellite to then downlink only a very small, in the kilobyte domain, the information on where the fire actually is. So time, latitude, longitude. And that's where machine learning comes in. And also what's the restrictive, or what builds the restrictions for if we can employ foundation models or not. And then the user gets notified, but through actually moving a lot of the processing into orbit, we can be much faster than anyone else. So usually satellites wait for a ground station overpass, then they downlink all the data, and then they have the processing on ground, which means that for MODIS, for example, or other satellites, the fire detections are a couple of hours old until you get them. That means for operational usage, you cannot use them anymore. And now I'll go into the machine learning use cases. I brought 2, and I would love to hear your input on where you would see foundation models fit into there, because I think there are a few spaces where it could fit. So here, active fire detection, you might think, well, it's a thermal anomaly. Basically, the hot pixels are a bit brighter and against that. So you have foreground against background radiation. And if you just employ a simple thresholding, it will give you good enough results. Well, it's not the case. So we clearly see shortcomings. And that's why we're also looking at all the model zoos. And here we took a SAG-former model that was pre-trained by NVIDIA. It's small, so it only has 3.7 million parameters. So we can actually deploy it on the satellite. And we compared it to a couple of other usual models like ResNet, MobileNet, and Efficient Nets. I mean, those are a bit older, but they still work. And our data set, so here you can see a region in Ghana where you see a lot of active fire detection because we have a lot of slash and burn activity in African regions. So that's always a good region to image. And with fire detection, you always have a stark class imbalance. So you only have a few samples that actually represent active fire. Then just really basic augmentation techniques. And we ended up with an F1 score of almost 90%. We always look at precision. So we optimize for precision just for our use case, because we want to be right when we tell our users that there's a fire. So so precision is still something that can be optimized. Our latest results, this is not the latest, but we're also almost at, I think, over 85% precision right now. But what we're seeing is with the vision transformer, we already get to pretty good results. So a foundation model would need to be better here than like 80–90% on our data. And that's the thing. So our data is a domain shift because it's not represented in the training data set. And we're testing foundation models all the time. So when a new foundation model comes out and you would say, fire detection, super easy task, they do not outperform our internal models yet. Cloud detection was mentioned before, also an interesting use case, because in thermal infrared, you don't see, so here's RGB, so an optical camera image. You have light cloud cover, but it's not reflected in the thermal infrared. So that means you already have data quality degradation. So your signal already has some noise in it, but you won't see it just from the thermal infrared image. So it's really important to have good cloud detection. We're doing it on thermal though. So here again, we work with class imbalance, we sample globally, we extended our own internal data set through Landsat 7 and only took the long wave infrared channel for training. And I brought some examples with me, again, like seeing on the left, the input image, then the thresholding, and then a couple of machine learning models. And what we see is here, this example in row 3, there's a lake. And the surrounding area is being classified as cloud by a thresholding algorithm. Because me as a tech manager, actually, I always have to defend myself. Why do I put resources into a machine learning project? Why do we need to spend hours and money there? Why do we collaborate with research labs and universities? We always need to, also in the commercial industry, you always need to benchmark. It just helps. I think that's what I learned from academia, and it always helps. Here we have mountain areas, classic cloud masking problem. It's also white, similar reflectance being classified as cloud. Then thin clouds are tricky. And so what we found there was that primitive approaches are worse, thresholding also worse, but with the machine learning models and also again small models, we got to a pretty good accuracy of 87%. So again, foundation model would need to be at like 95% for us to be used and integrated. And now I wanted to add something that's really unique about data science and our company is that we are optimizing for really fast runtime, so below 5 seconds on orbit. And we optimize it for GPU, and we package the models at ONNX. So everything needs to be really small, reliable, because we do a lot of parallel processing on board. So it's a pretty cool problem, but really restricted environment. And you also don't want to have spikes on your GPU during inference, because that risks to kill the satellite, actually. So you need to have a really stable inference. And so that also informs which layers you can actually use in your model, because some layers also in inference lead to spikes. And then I brought one other project, which is super resolution, that we've been working on. So there we took the original resolution and downscaled it to 30-meter GSD. They are multi-band and multi-image approaches. I won't go into detail in this talk, but this is also something else we're working on just to spark your imagination. And then one last area or product that we are working on is fire spread. It's being actively used. It's readily developed. And I wanted to mention it because there we actually combine physical and data-driven methods. So you have those components with fire spread. You have fuel, the fuel load, how much fuel is there available to the fire? What is the terrain like? Often that connects to accessibility. Often you have micro weather with when there's a mountainous area and the wind speed goes up, then wind is a fire driver and the initial fire perimeter. And there I could imagine, for example, to use an embedding, definitely for fuel, for a land cover, but then it's one part of the processor. And what we would need is we would need to evaluate internally if replacing our current fuel data pipeline through or with an embedding actually leads to significant and measurable product performance increase. So if the fire spread model then performs a lot better, well, then I would switch to embeddings. But if not, if we see similar performance, then why switch? And this goes along the whole prediction chain. So fire spread modeling is an hourly prediction that's already live. Then we also do daily prediction or daily hazard forecasting. There we work with NASA JPL, and we also work with NTUA on seasonal fire hazard forecasting. And that's interesting because especially the hazard forecasting products or projects leverage our data archive way more than our detections. So this has been a shift for every company, I would say, on the globe that produces their own data. So I think data sovereignty is where the value of commercial company in the moment lies. So if you have your own data, you understand your own data, that's way bigger advantage than it was a couple of years ago, because there it was like, how AI ready are you? And now it's really about data sovereignty. And if you want to access our data, there are 3 ways of doing it for German researchers. That's free through the DLR program. Then we'll be at ESA third-party missions available. There you need to write why you would want to use the data, and that's also free and available for researchers, or you contact us directly. And thanks a lot. I hope this was interesting and bringing you a use case to think about.